some will be operating at 3.3 volts. Okay, so 1.8 volt pins are mainly for data transfer, and 3.3 volt pins are generally to drive input or output. Generally, if you take your LEDs or your buttons, usually they'll be 3.3 volt. Okay, but for data transfer pins, they'll be under 1.8 volt. The main difference is the speed. Data transfer pins are enabled for high speed transmission, while these pins, that is the normal IO pins, they'll be having high delay, but they can drive larger voltages. So these are the different types of pins, as I mentioned: high range pins and high performance pins. Okay, high range pins are 3.3 volt. They support input output standards, PCCO voltage, and this is the maximum voltage it will support. Okay, and this high performance pin, it is 1.8. That's the maximum voltage. This is for high performance, as I already mentioned. And these are the variations of pins based on different families. Okay, in IO types, high range, high performance pins. In Arctic 7, all the pins are high range pins. Okay, for Kintex 7, most pins, you have a combination of both. And if you're looking at Vertex, and all the pins are high performance pins. So these are different clock management options available on your Xilinx boards. Okay, global clock buffers, local clock skew distribution, clock regions, clock management tiles. So these and all you must have already seen, like during synthesis and implementation stage in Vivado. So this is a clocking wizard. It's a very useful tool. If you suppose you're having your board will be having default input clock. Okay, so let's say it's around 225 megahertz. Okay, but you have a design. That design, let's say it's a counter. If you directly provide 200 megahertz into the counter, you won't be able to see it counting. It will be blinking so fast, you'll start feeling like it's not blinking at all. Okay, the rate of blinking will be too fast for the human eye to capture. So a situation arises where you have to reduce the frequency. So you can take in the default input frequency. You can provide you can take in 225 megahertz into the clock management wizard, and you can derive a 10 hertz, 10 megahertz frequency so that it will be visible for you. Like that, you can drive the design using clocking wizard. So this is the Zinc 7 series chip. Okay. So generally, FPGA evolved over a span of time. Okay, the FPGA has been evolving. It started with programmable logic. That is just the what are the hardware is there, it will be there. Okay. Afterwards, SOCs were added. That is processing system. You have a dedicated processor that's being added now. So once that is done, it is called an SOC, system on chip. After that, you'll be having multi-system on chip. Okay, and this is a communication protocol. That is the AXI interface. For our case, we're using ARM Cortex processor. Okay, so this is the entire structure of the architecture. Okay, we'll briefly explain this. So the main core area, this is the main processor here. Okay, it has various processing engines. It has a ARM Cortex A9 processor for our Zinc 7 series chip. Okay, it is surrounded by this AMBA protocol. Okay, this is an AMBA protocol. Through that, AXI protocol will be communicating. This is the programmable logic. This is the processor side. Okay, so PL to PS, some communication has to happen. That is being done through AXI protocol. So its main job is to enable communication between the two regions. And these are the various hardwares available to you. I mean, communication protocols: SPI, I2C, CAN, UART, GPIO, USB. So we'll see a small application of UART here in our Pink framework. Okay, I'll explain what the UART is doing there. This is another processor. Okay, this is a fairly advanced processor. This is a multi system on chip architecture. Okay, this is the PS for that application processing unit. That is, it is having 4 processors here. It's a quad core processor. Okay, so this particular board is highly capable. It can perform video processing as well. Okay, so there's a dedicated graphical unit here for that.